In this video tutorial, we will look at chemical reactions involving carboxylic acids and amines. One type of chemical reaction involving carboxylic acids is called esterification. This is the process of creating an ester. Now, this is a type of condensation reaction, which is a subcategory of a substitution reaction, whereby a carboxylic acid and an alcohol react to form an ester and water. When drawing out these chemical reactions, I prefer to put the hydroxyl groups on both sides side by side, so it's easier to visualize how these components come together. When converting from a condensed diagram to a line diagram, make sure you double check the number of carbons to ensure you've got the right number. So 1, 2, 3, 4 carbons, 1, 2, 3, 4 carbons, 1, 2 carbons, 1, 2 carbons. It's a very silly mistake to make, but it happens quite frequently. Alright, so now that I place the hydroxyl groups side by side with one another, anytime I see an H and an OH, I automatically think of water. So as I said, this is a condensation reaction. Water is going to pop out, where the red part of this alcohol switches places with the hydroxyl group that was on the carboxylic acid. So let's take the hydroxyl and the H, put it over here, producing our water molecule byproduct. And once these two are gone, it makes it easier for us to visualize how these two pieces will come together. And here we see the ester group matches up with the one we see over here. We have 1, 2, 3 carbons to the left of the carbonyl group, so 1, 2, and 3. And 2 carbons to the right of the ester functional group, so 1 and 2. And the water byproduct as well. Alright, so unlike the textbook, how they place the OH groups on opposite ends, I prefer to place the OH groups side by side. That way it's easy for me to visualize the OH and the H combining together to make water, and how to connect the two pieces together to make an ester. So, looking at our flowchart, we see that carboxylic acids and alcohols must combine together to produce the ester. This is a condensation reaction, which is a subcategory of substitution. It's also known as esterification, and in the process, water pops out as well as our ester. Heat and sulfuric acid are requirements for this reaction to proceed, with sulfuric acid acting as a catalyst. Now, this reaction is reversible through a process known as hydrolysis. So while esterification has the water molecule popping out in order to form the ester, we can reverse the reaction through hydrolysis by putting the water back in to split up the ester functional group. So the OH group from the water gets added onto this carbonyl group here, and that's where it is. Meanwhile, the hydrogen gets latched onto the oxygen bridge, producing a hydroxyl group on the alcohol side. This in turn splits the ester back out into its alcohol and carboxylic acid components. The reason why I don't show this explicitly with arrows on my diagram is because it would just get too messy and crowded in here. So I just wrote down this little note: reversible via hydrolysis with heat and dilute hydrochloric acid. As we've seen previously, alkyl halides can be used as a delivery device. I like to pretend the halogen, in this case iodine, acts as the truck, while the alkane, in this case an ethyl group, acts as the cargo for the truck. When you react this alkyl halide with ammonia, a substitution reaction occurs, where the alkyl group, in this case an ethyl, switches places with the hydrogen that was attached to the ammonia. So it's like the truck is dropping off its cargo onto the ammonia and picking up a new cargo, creating the hydrogen halide, hydrogen iodide. And now you have attached the ethyl group onto this ammonia, creating an amine, in this case a primary amine. Now, as a reminder, this is considered to be a primary amine because the nitrogen is attached to only one other carbon. If I want to make it a secondary amine, I got to attach another carbon to the nitrogen itself. And this can be done by repeating the process all over again. The only difference is, instead of reacting the alkyl halide with ammonia, we will react the alkyl halide with that primary amine we produced in the previous step. Once again, a substitution reaction occurs where whatever is in this cargo hold latches onto the primary amine, and the hydrogen latches onto the halogen, creating your hydrogen halide, and then now your secondary amine. And again, it's called a secondary amine because there are two carbons now attached to the central nitrogen. Again, as a reminder, whatever you put in this cargo hold will be latched onto this site over here. So in this case, it's an ethyl group. But if I used a propyl group, then the propyl group would be added on. If instead it was a butyl group, then a butyl group would be added on. Or if I had a pentyl group, then a pentyl group would be added on. So again, whatever is inside this cargo hold will get latched on to this site. All right, so you've made a secondary amine. I think we all know how to make a tertiary amine, one where there are 3 carbon atoms attached to the central nitrogen atom. And that, of course, is to repeat the same reaction all over again. So once again, whatever's in this cargo hold will be latched on to this final site over here, will be substituted in. So to summarize, if you have an alkyl halide, your delivery device, and react it with an ammonia molecule in a substitution reaction, whatever is in the cargo hold will replace the hydrogen that was here, creating a hydrogen halide and a primary amine. If you want to create a secondary amine, take whatever primary amine you created and react it again in a substitution reaction with another alkyl halide and repeat it to make a secondary amine. You want to make a tertiary amine? Do the reaction one more time and it'll latch on whatever is in the cargo hold onto that third and final hydrogen that was on the ammonia. All right, now that we know how to create amines, creating amides is just one extra step. Similar to esterification, where we took a carboxylic acid, reacted it with an alcohol to create an ester and water, amidification also requires the use of a carboxylic acid, but instead of an alcohol, we're now going to react it with an amine. This is a substitution reaction, specifically condensation, because water molecule pops out, and an amide is produced. Again, I don't like how the textbook has oriented these molecules. I kind of prefer seeing the OH and the H group side by side so I can visualize the water molecule popping out. So let's just redraw this, flipping the amine around so that the H and OH are side by side, allowing me to visualize the H and OH popping out, allowing me to connect these 2 bonds, and congratulations, you have now formed your amide bond. Alrighty, so to summarize, amines can react with carboxylic acids in a condensation reaction where water pops out. In the process, an amide is formed. Similar to esterification, this process can be reversed via hydrolysis with heat and sulfuric acid, breaking the amide bond and releasing the amine and carboxylic acid. Now, one thing to note, this reaction only works for primary and secondary amines. Tertiary amines cannot undergo amidification. The bond between the nitrogen and the carbon is fairly stable and hard to break, while the bond between the nitrogen and hydrogen is pretty easy to break. Substituting a carboxylic acid where the hydrogen is located here, here, or here is pretty straightforward, but trying to substitute a carboxylic acid where there are no hydrogens available, it's unlikely to occur.